Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we'll continue our example series related to the conservation of angular momentum. So the next problem that we have in this module is on the motion of a simple pendulum. So the problem says we have a particle of mass m, is suspended from a fixed point O by a light inextensible string. Okay, and the string is of length A, and it moves in 3D space. So we are talking about a pendulum moving along a spherical surface. So spherical pendulum. So this is a spherical pendulum, which means that we have now 2 degrees of freedom rather than 1. Okay, so then we have to show that the angular momentum is conserved about the vertical axis. So show that the angular momentum about the vertical axis through O is conserved. Okay, and we find this conservation law in terms of generalized coordinates theta and phi. So this is the regular theta and phi refers to the regular degrees of freedom in a sphere. Also, the problem says find the energy conservation. Find the energy conservation principle. Okay. So also it is given, there is some initial information given, initial condition information. So initially the string makes an angle alpha with the downward vertical. Downward vertical, and the particle is projected with a speed u. Okay, and u in the horizontal direction. Perpendicular to the string. So this is the detail which is given for this entire statement is related to the initial condition of the problem. We have to find the equation of motion satisfied by theta of t. So we have to find the equation which governs the the dynamics of theta. Okay, so let us try and draw a fairly accurate diagram here. So we have a pendulum which is attached to a string of length a. This is given here, and at any given time, the bob of the pendulum or the particle attached to this string is making is rotating about the surface of a sphere. So we have the angle it makes with the vertical is theta, and let's say we are given, so this is the plane, the circular plane, but this is of a slice of the sphere, and then there is this tension which is along the string, and then we have v theta, and we have v theta, and then we have v phi is the tangential direction, v phi is the tangential direction, and we have v rho. V rho is the perpendicular distance perpendicular to the axis of rotation, and then we have the downward displacement, the weight of the system mgk, and then what we have is the particle is moving anti-clockwise. So let us keep, that is the rotational angle is phi here. So these are the notations. And what else? So we have the tension acting along the string. So now let us try to tabulate what are the different forces acting on the pendulum. So the forces, the external forces are the weight of the string, the weight of the mass, and the tension in the string, and we see that the total moment is given by k0 is the perpendicular distance r cross mgk. Well, k0 is about the same, the natural axis of rotation which is passing through the center or along the sphere diameter. So then k0 is r cross mgk. So this is due to weight, and then plus the one due to tension r cross t. So now what we can do is that so what we have is that what is r? R is going to be the distance of the mass, particle mass at p from the origin. So this is our origin, and this is our r direction. So this is our r direction, right? So r hat, I would say. So we see that this quantity is going to be r cross t is going to be 0, because t is parallel to or anti-parallel to r hat. T is the tension in the string which is acting along the direction of the string, along the string. So this is along the r direction. So now we are left with the total moment is completely given by the weight of the system. And now so basically this one, so k0 is minus mg r cross k. So now if we take a dot product of this moment along the k direction, along the vertical direction, let us see what happens. So if we take k naught dot with k, we see that this is minus mg r k k. So minus mg r k k, and we see that this is going to be the standard dot. Well, this is the triple product, the scalar triple product with two vectors the same, and this is going to be 0, right? So what we get is, since this is 0, t is parallel to r. So this is 0, so t is parallel to r. Well, so this is 0 here. Hold on. So what we found was that the moment projected along the vertical direction is 0, which means that our angular momentum L naught along the vertical direction is conserved. So it's a constant. That is the conclusion. So it's a constant. So let us try and write down the angular momentum. So we want to find the conservation law in terms of yes. So we will try and write down L naught dot K. And we see that this is m rho times v phi. So again, L naught is m times rho. Rho is a perpendicular distance from the axis of rotation. The axis is along the vertical direction, and v phi is the tangential velocity, right? So m rho v phi, and we see that rho is, by geometry, it is a, it is going to be a sine. So rho is a sine theta. So rho is a sine theta. So a sine theta, and v phi is a sine theta phi dot. So this is rho times, so v phi is rho times phi dot, right? So and so what we get is this is m a square sine square theta phi dot, and this is a constant L. Right now, L can be found using the initial condition. At initially the velocity is u, so you have u sine alpha, because it is given that initially the angle that the string makes is alpha. So theta is alpha. So you get u sine alpha, and then the length of the string. Hold on. So something is not right due to geometry. What is the correct expression is m times a sine alpha, because alpha is the initial angle that the string makes and a is the length of the string. So a sine alpha times u is the velocity, right? And we get that we equate both these equations here, and what we get is the equation which is the angular momentum conservation. A sine square theta times phi dot is sine alpha times u. So that is what we have. Okay, so this is my angular momentum conservation. Let me call this as 1. Now the energy, the total energy, this is an isolated system, so the total energy is conserved. So what we get is the energy conservation is as follows. So we write the kinetic energy, which is half m v dot, half m v square, so a theta dot square plus a sine theta times a sine theta phi dot whole square. So a theta dot square plus a sine theta phi dot whole square. So that is those are my two components of the velocity. So v theta and v phi. So v phi square and v theta square, right? And then the potential energy is, we need to see how much is the mass is below the vertical, below the zero potential base. This is going to be, this particular distance is a cos theta. So the vertical distance is a cos theta. So my potential energy is minus mg a cos theta. So then we see that this is equal to the total energy, which is going to be half mu square minus mga cos alpha. mga cos alpha. So that is the initial energy. So that is the initial, from the initial condition. So that is my, so this second equation is my energy conservation. So notice that we have 2 degrees of freedom, theta and phi, and we have 2 equations. So the system is now fully determined. So now we can solve equations 1 and 2. We can solve 1 and 2. We have found both the conservation laws, and we can eliminate this variable phi. We can eliminate phi dot to arrive at the equation governing, purely governed by theta. So we get that the equations containing only theta is theta dot is u square by a square cos alpha minus cos theta times cos of alpha plus cos of theta by sine square theta minus 2ag by u square. Okay, so now, so this is what we have, and that is the end of this example. But we have, let us add one more part to this example. The last part of the problem says that find, so that's part D, find the period of the pendulum. Okay. So to find the period of the pendulum, notice that we can call this last equation as number 3. Equation 3 is already an equation governing the motion theta. All we have to find is we have to integrate this equation within a certain bound. So we have to find the lower bound of the integration and the upper bound of the integration, that is the lower limit of theta and the upper limit of theta where the pendulum rotates. Right, so that is what we will find. Now to find the minima of theta and the maxima of theta, we do a normal derivative test. We differentiate this equation number 3 to find the minimum. So what we do is, so it's already an equation of theta dot. So we set to find minimum or maximum. To find minimum or maximum, we set theta dot is equal to 0, and what we see is we either get theta is equal to alpha, or we get that cos alpha plus cos theta by sine square theta is minus 2ag by u square. Right? Okay. Is 0. So either this is the case, or so either the first factor is 0 or the second factor is 0. And let us call this second factor to be g theta. Right? Now what we can do is, we have found two values of theta. One is simple theta is equal to alpha, and the other one is governed by this equation g theta equal to 0. Now to find out which one is minima and which one is maxima, we have to go to the second derivative theta double dot. So to do that, let us now evaluate theta double dot, and let us try and evaluate this at value theta equal to alpha. So what we will see is, this is also equal to, after doing all the algebra, this comes out to be u square by a square times cos alpha by sine square alpha minus ag by u square. Okay, ag by u square, and what we see is this is going to be nothing but g of alpha. This is the same function as the second factor, g of theta evaluated, or so g of theta evaluated at theta equal to alpha. So what we see is that theta double dot, so from this expression star, so from star what we can see is that theta double dot, what is happening is, so this quantity increases as this factor is as we have that cos alpha by sine square alpha is greater than ug by u square. Sorry, ag. So ag by u square. So whenever this factor is positive, this factor g of theta evaluated at alpha is positive, we expect that theta double dot is increasing, right? Because theta double dot is positive, so it's an increasing function. So this is the value at, so theta double dot at theta equal to alpha is increasing whenever this happens. That's quite clear. And of course, it decreases when this factor is negative. So we can conclude that from here, we see that whenever this is positive, so in that case theta equal to alpha is the minima, right? Because these factors, this trend, the increasing trend with positivity and the decreasing trend with negativity, that clearly indicates that theta equal to alpha is the minimum. And theta max, so theta max is going to be the root of the other expression, which is g theta. So theta max is the root of g theta equal to 0, right? So that is what we have, and that's it. So what we see is, there is one more observation I want you to see is, if we look at g alpha again, this quantity, so g alpha is 2 times cos alpha, so there was a factor of 2 here, so 2 sitting, so 2 times cos alpha by sine square alpha minus ag by u square. So this quantity is greater than 0, this quantity is greater than 0. Now what we see is, if g, let us try and find out g of pi minus alpha. So g of pi minus alpha will come out to be only minus 2 ag by u square, and this quantity is less than 0, right? So we see that from here we can see that our theta max, which is a root, right, root of g theta equal to 0, is certainly going to be less than pi minus alpha, because this is where the sign of this factor g reverses, right? So the conclusion here is that theta max is certainly less than pi minus alpha. So now we sum up our discussion here. So our theta min is alpha, and this is of course less than theta max, less than or equal to, which is less than pi minus alpha. So the range is between alpha to pi minus alpha, or the exact range is between alpha to theta max, which we can find by solving the expression for g theta. And from there we conclude that theta, the pendulum oscillates between this range. Okay, so that is what we have. Okay, so then let us look at now the planar. Let us try and look at the rigid body motion, the planar rigid body motion, and let us see what is happening. So what we now discuss is the planar rigid body motion. Okay, so what we have is the planar. Of course, we are talking about the planar motion. So this is the generalized 2D equation. Generalized 2D motion. And we are talking about a system in planar motion. So planar motion, the idea is quite intuitive and should be quite clear. When we talk about the motion being planar, when the system of particles can be found in a single plane called the plane of motion, right? So when the system of particles move in a plane, right? And that is the plane of motion. Okay. So then it is, we can do some quick check as to what constitutes the planar motion. For example, listeners can see this as an example. For example, we have to find whether planar motion or not, right? So we see that the first case that I have for all of you is a cotton reel rolling on a table. The word rolling should be specially emphasized, because the moment we are talking about rolling, we know that there is no friction, there is no sliding, there is no friction force which is allowing the motion to slide. So rolling condition. So the moment you have rolling, perfect rolling, the cotton reel is going to show a planar motion, because, and the plane of motion is the plane to which the wheel is perpendicular, to which the wheel's axis of rotation is perpendicular. So the answer here is yes. So so then the other example is, how about earth, right? So earth, well, typically earth is rotating about the sun. So here we have the sun and the earth. The earth is rotating. A naive answer would be yes. But notice that the earth's axis of rotation is not perpendicular to the plane of motion. The plane of motion, yes. So we cannot say that the earth is exhibiting a planar motion, because its axis of rotation, sorry, its axis, yes, its axis of rotation is not perpendicular to its motion, right? So the rotational, so the answer here is no, because the rotational axis is not perpendicular to the plane of its orbit. The rotational axis is not perpendicular to the plane of its orbit, right? So the rotational axis is not perpendicular to the plane of its orbit. And then the third is the case of a snooker ball or a billiard ball being struck on its side. The billiard ball being struck on its side. Again, the fact that the billiard ball is being struck on its side, we cannot expect that the axis of rotation of the billiard ball is perpendicular to the plane of its motion. So this is not a case of planar motion. This third example is very similar to the earth example, the second example. The axis of rotation is not perpendicular to its plane of motion, right? So the answer here is as well as no. Now the billiard ball, we will talk in detail about these billiard ball problems towards the very end, when we talk about gyroscopes, gyroscopes, and we will see how complicated this motion is. So well, I think we have few more minutes in this module, but in this, which I will take it to the next module, where we will discuss the equation of motion for this planar rigid body, exhibiting the planar motion. So thanks so far for listening. Thank you very much.